Good morning. Welcome to the ZOOMTOWN experiment, episode number 23. Last week's episode covered the theoretical or conceptual idea of how the program is going to come together. And from that, we're going to actually dive right into the control software today. One of the concepts that's very important to me on this project is coming up with a deterministic loop. A deterministic loop is a loop that runs consistently at a specific time interval. In the case of this, I initially wanted a 2 millisecond time interval, but with all the time required for all the other calculations on a Pico in MicroPython, that wasn't possible. So I bumped it up to 5 milliseconds, and that may or may not still be capable, but we're going to work towards that in the course of the coming weeks as we build this program up from where we'll be starting from today. Now, you might be wondering why I want to go with this deterministic loop concept, etc. I come from an industrial background, and in PLCs and CNC controls and so forth, and other motion control devices, it works out very effectively to have a loop that happens every so many milliseconds or microseconds, whatever the case may be, a deterministic loop. And that will help with prediction of where things will be at a given point in time. Now, this whole project is all about motion control. Everything we do in this program, every bit of information we receive, is to control motion so that the Zoomie can get from point A to point B. During that travel, it's going to be important for us to know where something will most likely be a half a second from now. And the deterministic loop will help us to achieve that. It simplifies some other things too. The mathematics for calculating things can be a teeny bit more simple. Other reasons, I like it. It's a style that I've tried numerous times and failed miserably in MicroPython. And in about, I'm going to say 6 weeks or so, we're going to learn one of the reasons why it is so difficult to do in MicroPython. But as long as you understand that is what I'm driving towards, you will then understand why I am monitoring a lot of time for the functions to execute and other operations to execute, because I need everything to get done that I want done within that cycle time for this loop. As mentioned, with the motion control, it's all about velocity, vectors, where you'll be at some point, how long it'll take to decelerate, all of that. And what I want to do real quick is to just quickly review a few pieces of information that will play very important and key roles. We've got a wheel diameter of approximately 1.56 inches. Our motor, theoretically, max RPM is 100 RPM. Our inches per revolution would be 4.9 inches and 9/10. So every revolution will move that far. So if I take that times the RPM and then divide by 60, this is my distance traveled per second, 8.17 inches. That's important. At any point, I am going to be, when I look at where something is, 1 second later, it'll be 8 inches further down the road. That's why all this is so important. Now, if we break that down from inches per minute at 490 into inches per second, we get our 8.17, but I'm more concerned in a more fine resolution with time. One important thing is the distance to travel the entire length on the long edge of ZOOMTOWN, which is 96 inches. It'll take 11 3/4 seconds. The distance for every millisecond that passes by at full speed, the Zoomie will move 8 thousandths of an inch, or 0.2 millimeters. Now, our loop will be running at 5 milliseconds, assuming I can stick with that. At 5 milliseconds, we would take 8 times 5, and that would give us 40 thousandths of an inch, or essentially 1 millimeter. So that is an important aspect of time and this deterministic loop. Another driving factor with the loop, let me get this up a little higher, processing time. If you remember, during the build process, or actually even before build, when we were testing out various components, we were tracking very closely how long it would take to perform a read of that sensor or device, and perhaps even do a little bit of the processing of that information. What I came up with was, on the sensors that we ultimately went with, which are the TCRT 5000 photo sensors, Hall effect sensors, the AS5600 encoders, and the GP2Y OE03 time of flight sensor. Notice that all of those are going to come in at a millisecond or less, with the encoders taking a full millisecond to read both of them, but everything else would be less. So every time through my loop, I'm going to spend at least 1.65 milliseconds just reading the sensors. From that, I got a whole lot of processing to do and communications to do as well, and none of that's been factored so far. Now, for a comparison of why this was so important, going back to some of our first sensors that I immediately excluded, it took 18 milliseconds to read a time of flight sensor, one that I really wanted to use, but turned out, obviously, at 18 milliseconds, that's way too slow. And then a color sensor that I wanted to use for basically reading road signs. And that took 10.5 milliseconds. And on top of that, it was horridly unreliable depending on light conditions. So with that, right there, you see the importance of why those were excluded from this project. But from an important point of view, right now, 1.65 milliseconds is the absolute bare minimum amount of time for that loop to continually cycle and stay within some predictable range. In the code that you're about to see is actually a stripped down version of where it will be in your time frame about 6 or 7 weeks further. So in other words, what I've done is I built the program up to a point where it's very functional but not operational. And so I brought it back and stripped out everything. And then that way you're not going to get confused as I present this story of the program, where I have certain things a given way, but then in the next episode, some of those commands and so forth changed. So to me, it just made more sense to add clarity to the presentation. Now, I'll admit right away, my original plan for the program and the original code, I've made a lot of changes along the way, and I'm going to be pointing out a few of those in this process of explaining this program in its entirety, because there were some real interesting things that I've caught along the way. But again, I did not create this program as a perfect roll from beginning to end. Here is our program, our basic framework that I want. At the top, I normally put commentary up there and very important pieces of data. And the statistics area right in here, we'll be putting in our memory consumption, which is going to be very critical. This could get to be a very large program, and that could cause problems in the Pico. And the function time tracker, that will continually add to as I build functions, so we can keep track of how much time is being spent where. And we'll throw a little data into this during this explanation. We need to load a bunch of libraries. this will actually expand a little bit as we get further down the road, but I've got most of them already in here. I didn't want to strip everything back. We will be importing MicroPython, which is actually a library, not necessarily the whole language, and that will give me access to memory calculations and information. Math, we got to do some more than basic math operations, primarily trigonometry, etc. We need to have access to the machine components, which means essentially the pin, each pin, PWM for our signal we need to control motor velocity, analog to digital conversion for several sensors, and I2C interface. We also need to import from machine our watchdog timer and this frequency timer, and that will make sense later on. From time, I'm going to import sleep, so I've got ready access to use just a sleep command, and I'll be using a variety of these, a lot in testing and less so in the actual program. We will also import the entire time library because I need to do some cycle time calculations and I need other functionality in there for that. And finally, we're going to import an AS5600 library that is used for the encoders. Moving on to the next section, this is where I'll be placing the code for the networking and the MQTT communications functions and configuration data. After that, as you can see, I believe all of the hardware is defined here and initialized here. We've got our LEDs for front and rear status LEDs. They're bicolor, so we get 2 outputs per LED. We've got a button on the actual Zoomie. I'll show you those real quick here. This is the button that I'm talking about, and that'll have a very limited person because there will be very few opportunities to actually push this button while it's rolling around in ZOOMTOWN. This is the back side red-green LED, and it's going to be very hard to see here. That's the front side red-green LED, and I can utilize them the same or separately, and right now their use is very, very limited. I don't have a full idea how I want to use those 2 LEDs. I just figured while it's moving around I may need to communicate something, I just don't know what yet. Our motor controller requires a speed variable that will be a PWM signal, one for each motor, left and right, and then the frequency that the PWM signal would operate it at, 1000 hertz, and then we need 2 pins for each motor to tell it which direction to rotate to go forward or reverse. We have 2 Hall effect sensors, and those work like a typical digital input or output. It's either on or off. We are activating a pull-up resistor, an internal one, so that it's held high, and when the magnet detects something, or when the Hall effect sensor detects a magnet, it gets pulled low. The CAS sensor, the collision avoidance sensor, we're using the analog to digital output of that, or I'm sorry, the analog output of that to determine distance. It has another interface too, but this proved to be very fast and very efficient. Then we've got 2 line sensors, a left one and a right one, and those are assigned to ADC channels 1 and 2, and again that is an analog to digital conversion pins because it is an analog output from the device. After that, I'm going to interface or configure our I2C interfaces. Not any real magic here, nothing exotic or different. It's just that both of the encoders use I2C. Both of the encoders have the same device number. So I have to use two different channels. I'm using 1 and 2, so I got to be on separate pins and separate channels. And that's why I picked pins 0 and 1 and then pins 2 and 3, so that each encoder can communicate, have the same I2C address, but we're using two different interfaces, and that's how we get around that issue. We're going to run at 400 hertz for the frequency, 400,000. And that's worked fine, no problems with that. And then I just print out the data from the scan to check the status of these two I2C interfaces. And then that way, and during power up, you can kind of monitor this as long as the cable's plugged in. Then I'm going to start up and configure the AS5600 encoders. Technically, at this point in the original or the core framework, we don't really need to do that. I just left it in as a way to show you where this will be, and it'll be ready for when we get to it in about 3 or 4 videos. We'll have a left encoder and a right encoder based on our library and I2C interface. We're going to scan for the address. We will then, let's see, we got to write the startup positions for both of them. We need to know where an encoder starts, because these are absolute encoders. They are not incremental encoders, meaning that the count will go from, off the top of my head real quick, I think it's 0 to 4096 or something. We'll get into those details a little further down the road. So for every revolution, it goes from 0 to maximum value, back to 0, maximum value, and so on. So we need to have a starting point from which we can calculate how far the Zoomie moves. And that's all of that. And again, we'll go into that in greater detail when we get into motion control. Now, the next section is some people hate it, some people don't mind it, global variables. I wrestle with whether I want to go with class data or a fully class or object-oriented program, etc. And I always default back to my old ways. And I have no trouble with using global variables, and hopefully you folks don't mind. I will not explain all of these right now. I'll introduce these to you as they are needed by future program functional implementations of the program. But as you can see, there's a whole lot of stuff here in global variables relating to velocity, signals or states of signals coming from the scheduler, positional data. There's a lot of stuff that we've got to keep track of and constantly perform calculations on. But as you can see, there's quite a few, and most people are probably just screaming at me now, but please bear with me. Now we're down into this area of the program where you'll see placeholders for more functionality. This will be where I'm going to put all of my velocity control functions and calculations, or at least the vast majority of them. This area is a placeholder for my position handler. Everything that has to do with calculating position, distances, etc. Our very simple routines here for the Hall effect sensor to detect the status of a magnet, etc. This area here, as you can see, is coded into our foundational program. It's a very simple function. It's going to take in a color, and based on that color, it will set the LED. Based on that color, it'll set the LED values for red and green to either on or off. These are bicolor LEDs, so you've got to be pretty careful that you turn one state off, turn another one on, etc. But this is how I will switch between red and green. And off, I should say. We'll be working with this a teeny bit here once we get through all the explanation of code. And you'll also notice that after each of my actual functional blocks where I'm doing things, I'm generally trying to add in some print statements so I can monitor the implementation or activation of each of the features. That's more for debugging, but it can be handy in other aspects too. We'll get down to here. This, we're going to activate this here in a little bit. This is the watchdog timer setup. I called it WDT. Seems logical for watchdog timer. And we're going to set it for 1 second. And we've got to feed that with the WDT.feed call. And then that will reset this timer so it doesn't time out. Should it time out, this will reset and restart from the beginning, the whole program. So you'll see these WDT feeds all over the place in this program as it develops. This routine right here, right now, this button, the push button, is used to actually, the way I want to use it is after this powers up, the code powers up, I want it to stop at this section of the code before it can do anything. And then I will initiate any motion to occur by hitting that button to allow it to continue in the program. It's just a fail-safe right now. During testing, anything can go wrong, so the Zoomie could go taking off if I'm not stopping it at this point. And I might be 10 feet away and not be able to catch it before it rolls off the end of ZOOMTOWN and crashes onto the floor below. Here is the motion segment processor location. This is where I'm going to put the code that will take a command, a motion command segment, and then we'll turn that into codes that are useful to actually cause motion with the Zoomie. The trip executor steps through the whole list of the driving instructions from the start point to its destination. In here we've got this statement, MicroPython, that's that library I imported, and it says meminfo. When we run it, this will print out the data about the program memories, or I should say the Pico's memory usage in stack and all that. It is important to monitor that, especially when you expect a program to get large in size or complex. If you start hitting any limits anywhere, you need to reconsider your methodology and start reducing size. That's why that's there. That probably will be disabled when we get to the final phase of the program, because at that point it'll be running and we won't have to worry about it. We've got a couple of counters here, L counter and MQ counter. Those are really more needed in testing and debugging right now, and you'll see that be utilized. In fact, there'll probably be a few more as this whole program develops in the coming weeks. This is our loop. I'm calling it a regulated endless main loop as a reminder to myself. Here's that L counter getting incremented. And I'm going to right here say main loop start. This will tell me at the start of the loop the current time in microseconds. I'm going to be timing this to the microsecond. I am also going to record what I'm calling the very first element of the program. And this variable here will be used to calculate, or used in the calculations, how long it takes for all these other tasks to be performed. This is where I'll put the positional feedback from processing, the data, or perform that from here. Calculate the center line distance to go. That one's always really important as I'm moving along anywhere. I need to know how much further I have to move so that I can then perform calculations for deceleration and so on. I need to handle any of the velocity control inputs and have those be performed. I need to perform communications with my MQTT. This guy right here, I'm feeding my watchdog timer. And right now, of course, it's disabled. It's commented out, but we're going to play with that in just a few minutes. The end of move detector. This is only a temporary holder right now, and this will be used for the purpose of stepping through the trip executor. So we'll know when one move finishes and the next one should be started. And then we get to CP7 is like CP0, and that is the seventh phase of all these other operations. That'll make more sense as we move further. These lines right here are, well, actually it's these lines, these three lines actually create the deterministic loop, limiting it to be no faster than 5 milliseconds. And how do we do that? We calculate the runtime of the loop by taking the time in ticks microseconds minus the main loop start. So this is the current time, and that's the main loop start point. Then we're going to go into a loop within our main loop. And this is going to be a do-nothing loop. All it does is waste time until we achieve a total of 5 milliseconds. So while the runtime is less than the main loop cycle time, which is defined all the way up here, right here, main loop cycle time set at 5,000. So all the way back down here, we're going to keep looping while our current runtime, our current cycle time is less than that. If it isn't greater than that, it'll calculate a new runtime based on these two calculations, or on this calculation, current time minus the main loop start. And then finally, when that breaks out and the runtime exceeds the main loop cycle time, our 5,000 microseconds or 5 milliseconds, it'll break out of the loop. And then most of the time, I'm printing out that time difference between those two so that I can make sure I am running truly deterministic. If this value that I print exceeds 5, then I know my loop is running longer than the 5 milliseconds. Now in truth, because just that, the time to execute that, there's microseconds of time wasted, and I'm not overly concerned about 10 or 20 microseconds because of that. So yes, I am aware some of these things aren't absolutely to the microsecond accurate, but I am getting exactly what I want. And we'll see that run here in a minute. And then finally, when this is all done, there will be a way out of this loop, and we will adjust the run velocity back to 0, 0 so that the Zoomie just don't keep moving along should we abort at some point along the way. And then I clean things up with ending a program. Then I've got this commented code right here, and I call this my process time checker. It's just a boilerplate where I'm going to essentially do the same thing here, but very focused on one function or even a single line of code, so I can drop it in my code and measure the time it took to perform some action. Again, we just get the start time, we perform our action here, we get the end time. Both of those are in microseconds. I get the delta time by getting the difference between our start and our end, and then finally I print out the delta time in microseconds and then milliseconds. And that way I get an accurate measurement. And I can copy this and paste it into my code everywhere, uncomment it, and then wrap it around the function or piece of code that I actually want to test. And this has worked quite reliably. So that is our whole framework, and now we'll just play with a couple of things so you get an idea of the watchdog timer. And if you're curious, I'll have a link below. I've done a longer video on that, so we'll just kind of gloss over it here, and I'll have a link where you can go get more detail. Now diving back into the code, we're going to activate our watchdog timer and also my button. And as a reminder, this is the button that I'm referring to. It's a momentary push button. You'll notice that I've got a cable hooked up now. I've got batteries in here because with all the sensors in that, the Zoomie will not run alone with just our power coming through the USB. You've got to have the battery pack running as well. Now, with the watchdog timer, the thing to keep in mind, it will reset the Zoomie or reset the PicoW to start the program running again. In our case, the program name is Zoomie-01-A.py or PY. So it won't restart, but you will see the effect of everything here once I get the program running. So now what it'll do, the program will boot up, it will go through, it will print out memory data, let me know that the encoders are happy, and it'll activate the watchdog timer, feed it right away. It'll get caught up in this loop here, and it'll flash our status LEDs. Both the front and back should be flashing, but the back one is currently broke. I somehow magically shorted it out or overvolted it somehow. And so it'll stay in that loop, and it's going to get fed right here. The watchdog timer will get fed right here. So I'll press the button, the value will go false. I'll be pulling it to ground. It'll break out of this loop. It'll go into the main loop, and it'll print out, I changed out the print statement so it's a little more legible. It'll print out the runtime for our main loop so you can see the variations on that. It'll run for approximately a second, and then it's going to die because nowhere in the main loop am I feeding the watchdog timer. Okay, let's give it a run and we'll show you what I mean. Okay, we're running. We see that we got our information about the encoders up and running. My front LED, well, it doesn't look like red and green on camera. Let's see if I got a gel here. That might make it a little more visible on the colors. These cameras don't like LEDs very much. I will then press this back button. You'll see that the light will go off, but more importantly, watch the code. And there it was, the watchdog reset the process. Now let's take a look at the output that went in. We'll scroll back to the top here. This is the information right here that I want to keep track of with each iteration of the program. That's all my memory data and stack sizes. That's all this data here. It tells me the stack, current amount, out of X amount, memory used, free, blocks, etc. I'm really paying attention to this one right here because I think that'll be tell me more of the story than I need to worry about the rest of them. So I don't want that to get really ridiculously low. Right now we've got a long way to go before we start really knocking away at that one. Then that covers this data right here. I press the button, and then this is being printed in the main loop, and you'll notice that it's running fairly consistently. And I usually see a peaker of about 15 milliseconds. Here we go, or microseconds rather. So that's 5 milliseconds and 15 microseconds. And I really am not going to concern myself with 15 microseconds of deviation. Oop, there might have been a 22. Oh my goodness. Again, not a real big issue, but what happened after a second expired, then it hit the exception while running, and then that is the trigger for the watchdog timer to restart the program. So all around, that's essentially our base or our groundwork for the entire Zoomie program as we keep building on it. I would like to show you one more thing, so give me a moment to put that together, and that'll be, I'm going to disable some of this other stuff, and then I'll show you how I'm going to calculate cycle times for different functions, etc. Okay, now that I got the code modified, I've turned off the watchdog timer and I've turned off the button press in this area, just speed things up. It's not needed for quite a while further down the road, so we'll turn it off. Now this code here, oops, wrong button, and this one. This code here was our start time for before I do the set status LED state function, which was this function right here. I'm going to set the color to off, meaning it'll run this part of the code. So realistically, that'll be ultimately the longest portion, because it'll have to get through that test, then this test, and execute that code. So that should be the longest cycle time there. And then we record the end time. We use the function tixdiff, which will give us a very accurate reading of start minus end. Put it into delta t, we'll print that, and that's microseconds. I'll divide it by 1,000 and show you what that is in milliseconds. So let's give this a run. We'll let it run for just a brief second or two. And I added a break in the loop down below here by using that same button again. That exited us out. And I got an alarm because this function does not exist. So let's scroll this guy up, and we will see that our function to set these LEDs takes 0.1 milliseconds every time, and then our deviation drops to, I think, 97 and 106 or 7. 109 was my peak. So you'll see that even a routine just like that, where we're just going in and doing exactly the same thing over and over again, will take different periods of time. Almost always it's in microseconds of difference of time. So I don't really get too worked up over that. Now you'll also notice that even though I added another 1/10 of a millisecond of time to the main loop, you'll notice that my main loop trigger is still running at 5 milliseconds. And that's what I mean by a deterministic loop. Everything that's in there, that loop has to run as close as possible to 5 milliseconds every time. And that's what we'll be focusing on for a good portion of this whole project, is to make sure that that happens. Well, I think that'll wrap up this very lengthy introduction to our Python code framework for the Zoomie. Next week, we're going to dive into MQTT communications, and that's going to require quite a bit of stuff going on. I'm probably going to break that out into 2 videos, one to get everything set up and running, and then the next video would be how we can communicate between that and, well, of course, the broker, and ultimately over to the scheduler. That'll wrap it up. Thanks a lot for watching, and I look forward to seeing you next week.